Okay, I think we're about ready to get started here. Sorry for the wait. We're waiting for the sun to go down so we could sort of see the screen a little better. Welcome to the July edition of Second Saturday Stars here at the McCarthy Observatory. My name is Mark Polanski. I've been a volunteer here at the observatory for 14 or 15 years. I specialize in taking pictures of things in the sky, like galaxies, nebula, planets, and take measurements of asteroids that could threaten Earth. I'm also a spaceflight enthusiast. I'm interested in the engineering of all things that get launched from Earth and journey around our home planet and beyond. Space telescopes are particularly interesting for me, bringing together astronomy, astrophotography, and spaceflight with some incredible engineering. This particular telescope is also named for an incredible person who broke down barriers in several ways, ultimately making the case for space-based observatories to become a reality, notably the Hubble Space Telescope. This earned Dr. Nancy Grace Roman the title Mother of Hubble, and her legacy will extend into the cosmos next month with the launch of the Nancy Grace Roman Space Telescope. So tonight I thought it timely to talk about Dr. Roman and her namesake telescope, starting off with who is Dr. Nancy Grace Roman, and why was she important enough to have a flagship NASA telescope named for her? I'll talk about what big questions this new space telescope will answer, and what instruments and capabilities it can use to help answer those questions. We'll compare the Roman Space Telescope to the other big space observatories to see how it stacks up, and go over the launch details, when, where from, where it's going, and how it'll get there. Nancy Grace Roman was born in May of 1925, and left us in December of 2018 at the age of 93 years. As a child, her family frequently moved around the country, following her father's work as a geophysicist for an oil company, ultimately settling in Baltimore, Maryland, when he took a job with the U.S. Geological Survey. Her mother was a music teacher and would take Nancy on nature walks, where she fell in love with the stars while learning about the constellations. Nancy started an astronomy club in 6th grade, teaching classmates once a week about constellations from books they found. By 7th grade, she knew she wanted to be an astronomer. She attended Western High School in Baltimore, graduating in only 3 years through an accelerated program. Roman then attended Swarthmore College, wanting to study astronomy. The Dean of Women was not encouraging, saying to her, "If you insist on majoring in science or engineering, I won't have anything more to do with you," and referred her to the astronomy department chair, Peter Van de Kamp. At first, he too was hesitant, but eventually did teach her astronomy. She learned to observe the sky using 2 previously defunct student telescopes, which helped her get a feel for instrumentation and have some fun playing around with observing techniques. Her sophomore year, she began working on campus at the Sproul Observatory, processing photographic plates and learning astrometry, or the precise measurement of stars and things in the sky. She graduated in 1946, and Van de Kamp must have been impressed. He went from hesitation to teach her at all to recommending she continue and go for grad school at the University of Chicago. One month later, she did that. She started grad school at the University of Chicago. Roman found the classes to be easier than Swarthmore, so to challenge herself, she took on 3 observational astronomy projects in addition to her classwork. Some professors were still dismissive of her, one of which didn't speak to her for 6 months. Despite this, she earned her PhD in astronomy in 1949 after just 3 years. A few months later, she was invited to be a research associate at Yerkes Observatory by the same professor who didn't speak to her for 6 months. There, she studied stellar spectroscopy, producing some of the most highly cited research papers of the time. She was offered research positions at several universities, but turned them down because they lacked instrumentation, meaning telescopes, something that was very important to her. Roman ended up leaving academia because of a lack of tenured research positions available to women. The director of the Yerkes Observatory, Gerard Kuiper, of Kuiper Belt fame, recommended Roman for a position at the Naval Research Laboratory studying radio astronomy. The Naval Research Lab had an early lead in the new field of radio astronomy. In 1951, they had a 50-foot parabolic antenna, the biggest of the kind at the time. Dr. Roman had an advantage at the Naval Research Lab of being one of the few researchers with a classical astronomy background. She was often consulted for other projects, including Project Vanguard, which was the United States' attempt to launch a satellite into space for the first time, in response to the Soviet Sputnik satellite. Her consulting work on Project Vanguard was pivotal in introducing her to the idea of space-based astronomy. The ability to launch things into orbit around Earth unlocked the potential of placing telescopes outside of the blurring, scattering, and filtering effects of Earth's atmosphere. After a few years at the research lab, Dr. Roman was asked if she knew anyone interested in creating a program for in-space astronomy at this new organization called NASA. She took that as an invitation to apply and accepted the position. Despite her years of experience, her reputation, and international recognition as an accomplished scientist, she was hired by NASA as a new PhD graduate because her previous work had been so underpaid it was not recognized as employment. By 1960, she was serving as NASA's Chief of Astronomy and Relativity, NASA's first female executive. Even with that position, she still sometimes could not get past security without explaining her credentials. Reflecting on her career in science, Roman joked, "If I hadn't been stubborn, I would have been talked out of it years earlier." Much of Dr. Roman's role at NASA revolved around traveling the country, giving lectures at astronomy departments, discussing what NASA was developing and what they were trying to do. She was interested in finding out what astronomers wanted to study and to educate them on the advantages of observing from space, especially with groups convinced that money was better spent on ground observatories. She also established the idea that major astronomy projects would be managed by NASA for the good of the broader scientific community, rather than individual experiments run by specific groups or scientists. Basically, NASA was to coordinate access to space-based and other high-impact observatories based on the merit of the project proposal. This philosophy led directly to the creation of the Space Telescope Science Institute, the organization that to this day manages time and science objectives for NASA's flagship space observatories, including Hubble, James Webb, and in just a few weeks, the Roman Space Telescope. Dr. Roman led the Orbiting Astronomical Observatories program, developing the very first space telescopes ever, with OAO2 becoming the first successful space observatory. And while the scientific return of the OAO program was immense, the orbiting satellites were also used as testbeds to develop the technology to accurately point, maneuver, and communicate with telescopes in space. Years later, one of the last programs Dr. Roman worked on at NASA was the Large Space Telescope. Engineers at NASA had proposed several radical astronomy programs, from a telescope on the moon to a manned observatory in orbit. Roman had already proven the viability of remote space telescopes via the OAO program, without the complexities of landing on the moon or the risk to humans trying to operate a telescope in space. In 1969, the National Academy of Sciences performed a study on the viability of a 3-meter class telescope in space, and basically said, "Yep, it looks great, NASA, go for it." In 1971, Dr. Roman set up the Science Steering Group to lay the groundwork for what would become the now beloved Hubble Space Telescope. She pushed relentlessly for this idea, solving technical problems, drumming up congressional support, finding funding, and inspiring so many people with the possibilities a big telescope in space could realize. Just under 20 years later, that dream became a reality with the launch of Hubble on April 24th, 1990, in the payload bay of Space Shuttle Discovery. Dr. Roman's efforts to bring Hubble to life earned her the nickname Mother of Hubble. Later in life, she quipped that she didn't really like that title, as she thought it detracted from all the other people who worked so hard to make it happen. She said, "I think it would have existed sooner or later without me, but I think the timing was better when I got into it." Dr. Roman's passion for and excellence in astronomy, glass ceiling shattering, brilliant service at NASA, and undeniable impact on the future of space telescopes has more than earned her the legacy of a flagship observatory carrying her name into the cosmos. NASA bestowed this honor upon Dr. Nancy Grace Roman on May 20th, 2020, a year and a half after her passing. So let's dive into the telescope itself. It features a 2.4 meter or almost 8-foot diameter primary mirror, the exact same size as Hubble. But the focal ratio is much faster at f7.9, and I'll talk about what that means later. The Roman Space Telescope uses a special optical design called a 3-mirror anastigmat. The long story short is it uses 3 sets of mirrors to reduce or remove optical problems. Imagine taking a picture with your phone, where most of the middle of the picture is nice and sharp, but as you get close to the edges, things start to get stretched, smeary, and strange looking. That's sort of what happens to wide telescopes with big camera sensors. Having this more complicated optical design helps get rid of that problem. There are 2 main imaging payloads on board. The wide field instrument is a 300 megapixel camera with over 1/4 degree field of view. That's a little over half the size of the average full moon in the night sky from our point of view. It'll also have a first of its kind coronagraph instrument, a small field of view, high contrast camera and spectrometer with the ability to suppress the light from distant stars to help look for planets around them. This means we could potentially get some of our first direct images and spectra of planets around other stars. What can we learn with all that fancy tech stuff? Well, one of the biggest quandaries in astrophysics is the expansion of the universe. In 1929, Edwin Hubble discovered the universe was expanding, likely as a result of the Big Bang. Only 28 years ago, in 1998, we discovered the expansion of the universe is actually accelerating, not slowing down as once expected under Einstein's general relativity. Dark matter and dark energy are parts of the leading theories behind the acceleration. The Roman Space Telescope has 3 independent techniques to test theories about dark energy, any of which could help shed light on the increasing rate of expansion. It can also help answer questions about the potential for life in the universe. By taking a census of exoplanets, the Roman Space Telescope will find out how common solar systems like ours are, with inner rocky planets, a habitable zone, and gas giant outer planets. We'll also find out what kinds of planets exist in the outer reaches of other star systems. Are there more rocky Earth-like planets, or more dwarf planets like Pluto? Are there more ways a planet could be considered habitable, or what does it take to make it so? With the help of gravitational microlensing, it might even be possible to find exoplanets just a little bigger than our own moon. With the new coronagraph's ability to block out light from host stars, we can get our best look yet at our solar system's nearest exoplanet neighbors with direct imaging and spectroscopy. Rather than inferring composition by examining light from the host star, we'll be able to directly image and sample an exoplanet's atmosphere and determine what elements make them up. How does the Roman Space Telescope compare to the current fleet of flagship observatories? Let's start with the closest comparison, the Hubble Space Telescope. Both have the same size mirror at 2.4 meters, but Roman has a much faster focal ratio at f7.9 versus Hubble's f24. That alone means Roman would have a much wider field of view, but Roman also has a much larger imaging sensor, so it ends up with about 100 times increase in what it can see in the sky versus Hubble at very similar resolutions. So what does that mean in practice? Or the better question is, what does it look like? This is the Eagle Nebula in the Hubble palette, highlighting emissions from sulfur gas in red, hydrogen gas in green, and oxygen gas in blue. One of Hubble's most famous images is the heart of the Eagle Nebula, known as the Pillars of Creation, where new stars and planets are being born. The inner square represents what Hubble could see in that iconic photo. The outer white border is what Roman can see. That's what a wider field of view looks like. The astrophotographer in me can't wait to see what Roman can produce. And now for the relatively recently launched James Webb Space Telescope, by far the largest telescope in space thanks to its origami-like unfolding process. It sports a whopping 6.5 meter or 21-foot primary mirror at a reasonably slow focal ratio of f20.2, compared again to Roman's 2.4 meter f7.9 mirror. Webb sports some fairly high-resolution cameras, but with such a long focal length, the field of view ends up close to that of Hubble's, meaning Roman again has the ability to see much more. Here we have Webb on the bottom, with its field of view marked in the yellow squares, while Roman, pictured on top, is the combination of all the blue squares put together. Webb's field of view is not that different from Hubble. Roman can just see that much more of the sky. The other key difference between Webb and Roman is that Webb can only really see infrared wavelengths of light. It can't see green or blue. Roman can see visible light from red down to a deep blue, in addition to some near infrared, which makes it a great complement to Webb. The Roman Space Telescope is currently scheduled to launch on August 30th, a little over a month and a half from now. It'll ride to orbit on a SpaceX Falcon Heavy rocket from Launch Complex 39A at the Kennedy Space Center. Roman's also heading for the same neighborhood in the solar system as the James Webb Telescope. They'll be observatory neighbors orbiting Lagrange Point 2 together. Lagrange points are special places in space where gravitational effects from multiple bodies interact in unique ways. Lagrange Point 2 lies about 4 times farther away from Earth as the Moon, on the opposite side of Earth from where the Sun would be. What makes it a great place for telescopes is it allows objects to follow the same orbital period around the Sun as Earth, basically the same length of a year, while being far enough away from Earth to not experience any atmospheric effects, or have Earth looming over it, occupying a large amount of the sky, as is the case with Hubble in low Earth orbit. They are naturally stable points in space, requiring minimal propellant or fuel to stay in place over long periods of time. The Roman Space Telescope is expected to operate at least 5 years, with hopes of getting 10 or more years of science out of it. So, what did we learn tonight? We learned Dr. Nancy Grace Roman is a brilliant astronomer, a trailblazer, effectively the mother of the Hubble Space Telescope. She helped pioneer space telescopes in general and advocated heavily to make them a reality. It's fitting to honor her legacy and substantial contributions to both science and space telescopes as we know them today by naming this flagship observatory for her. We also know the Roman Space Telescope might help us answer questions about the expansion of the universe and dark matter and dark energy, along with gobs of new information on exoplanets to answer habitability questions. The Roman Space Telescope has the same size mirror as Hubble, but about 100 times the field of view, with a similarly large field of view compared to Webb. And it'll be launching next month on the 30th of August on a SpaceX Falcon Heavy rocket. Any questions?
How long does it take then if it launches on the 30th to get actual pictures back?
Oh, to actually get, sorry, the question is, after launching, how long does it usually take to get pictures back from it? Typically it's months, because it doesn't take long for it to actually get up into space and get where it's going. The problem is the commissioning process. It's a little bit less complicated than with James Webb because it doesn't have to unfold itself. There are still some mechanisms and things that have to unfold, but it's a way less complicated process than Webb. So typically it's a couple of months. If I had to guess, maybe 3 months, 4 months, but it could be as long as 6 or 7 depending on the exact process.
Commented that the universe is expanding. And how can we tell that if we can't find the end of the universe? I mean, what is the form of the expansion?
Okay, that's a great question. So the long story short is, we can look into space and we can see other objects. We can see galaxies, right? And I'm going to tie this together in a second, but on Earth, we experience what's called the Doppler effect. When like an ambulance is coming at you, it starts higher pitched, and as it goes past you, it ends up with a lower pitch. We can use that same effect with light. So we can look at galaxies that are far away from us, and we can look at the light coming from those galaxies. And the light from the galaxies will be shifted one way or the other. If they're shifted towards the red, it means they're moving in one direction. If they're shifted towards the blue, they're moving in another direction. I never remember which is which, whether it's coming or going from us. But by looking at all these galaxies, we can see that the farther away the galaxies are, the more redshift there is, which means the faster they're moving or the faster they're accelerating. So with all the survey telescopes we have now, we have a pretty good handle on how fast the universe is actually expanding. And we've seen over time, because as we look at further and further things, we're looking further and further back in time. And we can see that the further objects, I've misspoke before, the further objects have less of a redshift. The closer objects have a longer redshift, which means as we get closer to our point in time, things are moving faster. So working that out means that we've figured out that the universe is expanding and accelerating.
Do they know what we take a picture of first?
I don't think we do that. I don't think we know that yet. Usually they try to keep it under wraps, but it'll be something spectacular. They usually pick something good. Looking forward to it, though. Another good question. One theory is what's called the heat death of the universe. Basically, as things get further and further apart, the amount of energy in the universe is going to decrease over time, and eventually everything just cools down to the point where nothing is moving and there's no energy. I don't know that we know where that energy goes, but that's one potential outcome, you know, in innumerable number of years into the future. But you can Google that, look up the heat death of the universe.
If this telescope is going to last 5 to 10 years, we must have it planning ready what the next telescope is going to be. Do you know anything about that?
I did. I looked this up a little while ago, but I don't remember the details of it. I'm sorry.
They are planning.
Oh yeah. Generally, telescopes are decided in what's called a decadal survey. Every 10 years, NASA and all the big science organizations come together and talk about what their priorities are for the next decade, because they know that a telescope like this can take 10, 20, 30 years to develop. So there was a decadal survey a couple of years ago where they came up with some ideas of things they want to study, and they're now designing and building those telescopes to study those. All right. Well, thank you for coming. Join us next month on August 8th for our next Second Saturday Stars. And hopefully we get some clear sky and we can look at some things with telescopes tonight.